Well, let's apply these low entropy ideas now to something a little different. We'll start talking about frequency response. So here's another very simple little circuit, passive circuit this time. 2 resistors and a capacitor. The objective is to find the voltage transfer function, V2 over V1. So you can treat this as a voltage divider. And the formula is you take the bottom branch of the divider, which is the parallel R2 and C, and you divide it by the sum of the 2 branches, R1 plus the other stuff. And then you start grinding algebra. Now, first you multiply out the parallel combination. And here's one simple result worth remembering. A parallel R and C has an impedance which is equal to the resistor by itself divided by a single pole. And the value of the pole is the RC time constant. One line of algebra is the only thing that's missing in writing that answer down. The next line of algebra means you get rid of the internal fractions, because the objective is to write the answer as a ratio of polynomials in complex frequency. That is, you want the numerator to be in the form of 1 plus s squared plus s cubed, etc. You want the denominator to be in the same polynomial form. So here's the penultimate line, and one step left is you want to make the leading term 1, so you bring out the R2 from the numerator, you bring out the R1 plus R2 from the denominator, and you have to divide it into the second term, and once again you observe product over sum, which you identify as parallel combination. Well, it took about 4 lines of algebra to get there, and it was plain dog work just to get the algebra. So here's the easy way to do it. Use Thevenin's theorem to absorb the R1 and R2 into an equivalent, which reduces it from a 2-loop circuit to a single-loop circuit. Write the answer as a voltage divider, and there's the answer in one line. Same answer. No algebra at all, and it's automatically in low entropy form. Because by doing the algebra on the circuit diagram, it automatically came out that way, including the parallel combination of resistors, which in the other method you had to notice it in order to restore it. In this method, it came out automatically from Thevenin's theorem. Well, whichever way you do it, the next step is to identify the salient features. Salient features means the coefficient in front and the coefficients of the S terms. Because the coefficient in front has the interpretation of a gain, in this case a loss, but it's a gain factor. So call it some symbol like A1. The coefficient of S has the dimensions of reciprocal frequency, so you define it as the corner frequency. In this case, the capacitor together with the 2 resistors in parallel. So this is the normalized format, which is a simple case of expressing the frequency response in factored pole zero format. In this case, there are no zeros and there's one pole. And the coefficient in front is a flat gain. In this case, the flat gain is equivalent to the zero frequency gain. Because if you let S go to 0, the other factor goes to 1, so the gain approaches A1 at 0 frequency. So this is the basic building block known as a single pole transfer function. So the next thing to do is to look at the sketch of that function as a function of frequency. And the way you start doing the sketch is you look at 0 and infinite frequency and see what the final asymptotes are. As S goes to 0, the gain goes to A1. In this example, A1 is less than 1 because it came from a resistive divider. And we plot that on a dB scale, which is a logarithmic scale. So if A1 is less than 1, it's a negative number of dB. Then you jump to infinite frequency and see what the magnitude does, and it goes as 1 over S, or 1 over j omega, which is a reciprocal function. Since we've chosen double log scales, a reciprocal function is also a straight line, which is the red asymptote shown up at the top end. And that line has a slope of 20 dB per decade of frequency, which is just a complicated way of saying 1 for 1, or 10 for 10, because it's a simple reciprocal. If the frequency goes up by a factor of 10, the gain goes down by a factor of 10, which is 20 dB for a factor of 10 or a decade of frequency. I don't think there's anyone here old enough to remember the old-fashioned way of expressing that, which used to be minus 6 dB per octave. Some people do remember it. Yeah? Well, that was in the days where we did our calculations using log tables and slide rules instead of calculators. Because when we actually had to use log tables, pretty soon everyone got to remember what the log of all the integers was, just by frequency of use. And the log of 2 is 0.3010. And so when you convert that to dB, it's 20 times 0.3010, which is 6.02. So you forget the 02 and you call it 6 dB for a factor of 2 in frequency, which is 1 octave. But now no one knows about log tables anymore, so we call it 20 dB per decade. So. Okay, now these are the two asymptotes, 0 and infinite frequency. And in fact, this is one of the reasons we choose double log scales to show the graph. It's because we get a straight line at both ends. If we extrapolate those two straight lines, they intersect at the corner frequency omega 1. And in fact, that's why it's called the corner frequency, because it's the corner of the straight line asymptotes. Although the actual function for the magnitude does not go through that sharp corner, the actual function is the green line, and here's the full formula for the magnitude. When you have a complex function, because S is j omega, remember, the magnitude of the complex function is the square root of the sum of the squares of the real and the imaginary parts. If you evaluate that function at the corner frequency, omega equals omega 1, you get 1 over the root of 1 plus 1. 1 over root 2, which is 10 times the log of 2, 10 times 0.3010 is 3.01. You forget the 01 and you say that this is the 3 dB down point. So the actual magnitude at the corner frequency is 3 dB below the asymptote intersection. I get this overlay placed exactly right, I hope. Yeah. Well, everyone knows that that's the 3 dB down point, and really all you have to remember about the asymptotes for a single pole function are that you have the sharp corner of the asymptotes and the actual curve is a 3 dB down at that point. There's a couple of other points that are useful to know about also, because the only thing that you don't know by using only the 3 dB down point is that you don't know what is the frequency scale involved. You don't know how far this gradual curve is extending on either side of the actual corner. That's the reason for identifying another point, the 1 dB down point. Now, the choice of 1 dB, of course, is arbitrary, because the curve only approaches the asymptotes at 0 and infinite frequency. So you have to make an arbitrary choice of when you say the curve has approached the asymptote sufficiently closely that you can say it got there. 1 dB is a convenient number because 1 dB corresponds to a ratio of about 1.1. 1.1 is different from 1 by 10%. 10% is a typical tolerance level that you deal with in design from the point of view of specifications. It's a typical tolerance level for element values. So 10% is a good criterion. Anything less than 10%, you forget it, except in special cases. So since 10% converts to about 1 dB, 1 dB is a good place to choose on this picture to say this is the frequency at which the actual magnitude function has begun to deviate significantly from the straight line asymptote. Another way to express that is imagine yourself standing on the frequency axis and you start walking along the axis towards higher frequencies. But there's a fog around you and you can't see very far ahead. All you can tell is the slope of the ground under your feet. And the slope seems to be increasing. And the question you're asking yourself is, the slope's getting bigger, when am I able to say there is a corner up ahead that I can't see in the fog? So the 1 dB down point is that criterion. When the level of the ground has dropped 1 dB, then you can say there is a corner ahead, and it's a factor of 2 away. Because it turns out that when you substitute into this formula, 1 dB down corresponds to a factor of 2 away from the corner. And interestingly, this is exactly symmetric on the other side. If you're at infinite frequency and you're walking up this hill, and the slope appears to be getting a little less, when it's dropped 1 dB below the original slope, then you can say you're a factor of 2 above a corner frequency. Yet another way of saying that whole thing is the influence of the corner extends an octave below and above the position of the corner. The influence extends that far. If you're further away than that, you can't tell the corner is there. Now, why am I making so much fuss about this interpretation? Well, we're going to see a reason why that's important and a difference between what you get by looking at the magnitude graph from what you get in looking at the phase graph. So the phase graph is the next thing we need to look at. So we ask the same series of questions. If we want to sketch the phase graph of the single pole function, look at the extremes of frequency. At 0 frequency, the phase, which is the arctangent of the ratio of the imaginary part to the real part of the function, if omega is 0, the angle is 0. So the 0 frequency phase graph is horizontal at 0 degrees. Go to the other extreme. At infinite frequency, arctangent of infinity is 90 degrees. And it's negative because the function is in the denominator. So the phase asymptote at infinite frequency is minus 90. If you extrapolate those two asymptotes towards the center, they don't intersect because they're parallel. So we're reduced now to actually plotting the function, the arctangent function. And we typically choose linear degrees versus log frequency. And again, interestingly enough, the function turns out to be anti-symmetric around the corner frequency. That is, the shape of the curve, the green curve below the corner, is exactly the same as the shape above the corner, except reversed and inverted. So that much of the picture is what we have. But obviously we would still like to select a straight line approximation or a straight line asymptote that would represent how the phase function changes from 0 to minus 90. But we have to invent one. The first idea might be, let's find the slope of the arctangent function at the symmetry point, which is the corner frequency, And let's extrapolate that straight line until it intersects the other asymptote, and let's find what the value of that frequency is. Then we can mark it off on the picture, and when we want to make a sketch like this, we mark off that frequency, and then we can draw the straight line. Well, that's a possibility. I don't remember what that number is. And the reason I don't remember is I don't like it. Because there's a better one to choose. All I remember about that number is that it's less than 10 times the actual corner frequency. Well, since I don't like it, what happens if I make it 10? Which is what I've drawn here. What happens is that the red line that's actually drawn is a little shallower than the one I suggested first. The one I suggested first was the tangent of this curve at the symmetry point. But if I choose this one, it's a little shallower. Now this has the advantage over the one I suggested first, not only in that 10 is easier to remember than some non-round number, but it's also a better approximation. Because the first one, all of the deviation from the green curve is on one side of the original choice. With this choice, the deviation is split on both sides, which means the maximum error is less. So I have chosen an approximation which is in fact more satisfactory than the initial one I suggested. And it's easier to remember. So the way you do it is, if you want to draw a straight line approximation for the phase graph of a single pole function, you simply mark off 1 decade in frequency, and you draw a straight line going from the corner frequency to that frequency, and that's a very good approximation to the actual curve. The maximum deviation actually occurs at the asymptote intersection. And it's easy to evaluate that, because if you put in the formula omega equals 0.1 omega 1, which is where that asymptote intersection is, arctangent of 0.1, remember some high school trigonometry? Series expansion of the arctangent function. You probably don't remember it. The first term of the expansion is the argument itself, which is 0.1. Radian. 1 radian is 57 degrees. 0.1 radian is 5.7 degrees. That's not much of an error from the asymptote intersection. So those straight lines are pretty good approximations for the phase function of a single pole. And that's usually sufficient to draw all the sketches you need, just as the asymptotes are sufficient for the magnitude function. Okay, that's the single pole function. Now let's look at the single zero. The only difference between a zero and a pole is the 1 plus s function is in the numerator instead of the denominator, and I've already mentioned in the introduction that the only consequence of that is a vertical inversion of the magnitude asymptotes. Because moving a function from the denominator to the numerator on a logarithmic scale is the same as reversing its sign, which is turning it upside down. Now you see that the same thing applies to the phase graph, because the phase function for a zero is simply plus the arctangent of omega over omega 1. So it's simply the reversed sign from what it was for the pole, which is a vertical inversion of the phase graph, because that was already on a linear scale. So a zero gives a phase lead from 0 to plus 90 instead of the phase lag from 0 to minus 90. And of course all the salient features go along with it, including the 3 dB point and the 1 dB points, and including the phase slope, which is now plus 45 degrees per decade instead of minus. It's a simple vertical inversion of both the magnitude and the phase graph. Now you see why I made so much fuss about walking along the frequency axis and how far away from the corner the influence could be seen. The corner can be seen from further away on the phase graph than on the magnitude graph, because if you imagine yourself walking along the phase graph starting at 0 frequency, and you ask, when can you begin to see the corner? Obviously you begin to see it when the asymptote changes slope. But that's a whole decade below the corner, which is much further away than the octave on the magnitude graph. So the bottom line of that comparison is the influence of the corner frequency extends a decade above and below the corner in the phase graph, and it only extends an octave above and below the corner in the magnitude graph. That's a useful thing to know, because what it tells you is that the phase is a more sensitive indicator of the presence of a nearby corner frequency than is the magnitude. And it also tells you directly that if you have a corner frequency, its influence is going to extend further away in the phase graph than in the magnitude graph, and that's an important thing to know when we start talking about stability of feedback systems, where the phase margin is one of the important design criteria. Now, I mentioned reasons why we choose double log scales for magnitude and single log scales for phase. It's because of this vertical inversion property. The same thing, the same reasons, in fact, carry over into something else, which is cascaded transfer functions. Here we've got two simple low-pass RC networks. I put a buffer in between them just for simplicity to avoid any interaction. But the overall transfer function, of course, is simply the product of the transfer functions from each one separately. Each one of them is a single pole with two different values of corner frequency. Now, the magnitude of the total transfer function is the product of the magnitudes of the two separate functions, but when you express them on the dB scale, the product becomes a sum, because the log of a product is the sum of the logs, which means that simple superposition applies when you want to cascade two networks. The same thing applies for phase, because we plot it on a linear graph, because the total phase is the sum of the linear phases for each network separately. So superposition applies again in both graphs. As an example, suppose the first of those networks is this single pole function with a corner at omega 1, magnitude asymptote, phase asymptote is minus 45 per decade. Here's the second network. Exactly the same function, but a different corner frequency, omega 2. But if you want to find the overall transfer function of the two together, simple superposition applies, and the combination of the two looks like that. Both magnitude and phase. Notice that the phase graph is fairly complicated. If you looked at that by itself, it's got 1, 2, 3, 4, 5 linear segments. Looks sort of messy. But when you remember that all it comes from is the superposition of two basic building blocks like that, suddenly it's easily interpretable. Okay, we've got now the well-known building block, a single pole and a single zero. Now I want to introduce again the idea of inverted poles and zeros. There's a flat gain. Call it a mid-band gain again, just for simplicity. What I'm going to be emphasizing now is the relationship between the asymptote sketches and the factored pole zero forms. Because probably what you're used to doing is doing the algebra, getting the equation, finding the poles and zeros, and then drawing the sketch. What I want to emphasize now is the reverse process. Given the sketch, which locates the corner frequencies, which is the specification you have to build, that's the starting point, remember, the answer to the analysis. Given the sketch, the first thing to do is to write down the corresponding algebraic expression in factored pole zero form, so which is the reverse direction. So, starting with this picture, this is the flat gain. The expression that goes with it is simply A equals AM. But now, suppose we have some higher frequency corners. So suppose at omega 1, the asymptote bends upwards. That's a concave upwards corner. That's a zero. At omega 2, it happens again. So there's another zero at omega 2. At omega 3, it bends the other way. So that's a concave downwards corner. That's a pole. So the factored pole zero expression that goes with that sketch looks like this. The omega 1 is a zero, so it's a 1 plus s term in the numerator. The omega 2 is the same. The omega 3 is a pole. The 1 plus s term is in the denominator. As another example, suppose I have the same AM, but I turn the top picture upside down. Now the zeros and poles have changed places. And in the algebraic expression, they also change places. The omega 1 and omega 2 terms now are in the denominator, corresponding to poles at omega 1 and omega 2, and the omega 3 is now a zero in the numerator. So this is simply re-emphasizing the fact that poles and zeros are interchangeable, corresponding to a vertical inversion of the asymptote graph. But now, what happens if I make a horizontal reversal of that picture? Now, starting with the same reference expression, A equals AM, something different happens as I go towards lower frequencies. And it's a horizontal reversal of the previous picture, which corresponds to inverting the S terms themselves. So, starting with AM, which corresponds now, notice, to the infinite frequency limit of this formula. If you let S go to infinity, this additional factor goes to 1. A goes to AM, which is the proper value at infinite frequency. As S comes down, when you approach omega A, you have a concave downwards corner, so it's a pole. So the 1 plus term is in the denominator, but because we're going downwards in frequency, it's an inverted pole, so you write it as 1 plus omega A over S. Then you continue down. Same thing happens again at omega B, so there is another inverted pole, a 1 plus omega B over S term in the denominator. And finally, concave upwards corner at omega C, so that's a zero, but it's an inverted zero because you're going down in frequency. So it's simply a matter of what is the reference direction of the change of frequency. If you're moving up in frequency, poles and zeros are in so-called normal form. If you're going down in frequency, they're in inverted form. Now, to give you a little practice of that, I'll take that away and I'll turn that one upside down, and you see that result is missing from the notes. That's because you get to write it in. So remember, the principle is write the flat gain first, A equals AM, because you're going to choose that as the reference gain. And you look up in frequency and see if there's any corners, and there aren't in this case. So you look down in frequency, and the first thing you encounter is a concave upwards corner. And the only two questions you have to ask yourself are, does it bend up or does it bend down? And are you going up or down in frequency? And you answer those two questions, and it tells you what factor to write in each case. Okay, let's look at that. Just ask those two questions sequentially. If you look down from AM, you see a concave upwards corner, so it must be a numerator factor, but you're going down in frequency, so it's an inverted zero at omega A. Omega B is the same thing again. And finally, it bends downward, so it's a denominator factor, and you're still going down in frequency, so it's an inverted pole. Okay, now I'll go back to the previous case, which is that, and it has this function. But of course you can have normal and inverted poles at the same time. So here's a frequency response with one flat gain. Take that as reference by writing it in front. And now when you look down in frequency, you have the inverted poles and zeros. When you look up, you have the normal poles and zeros, and they're all there together. Okay. All the examples so far, we've had one flat gain. So let's look at some special cases. Here's a case where there isn't a flat gain. And if we want to write the factored pole zero form, we have to have some means of locating the vertical position of the whole picture. So what you do is you just take some arbitrary point on the asymptote, which has a corresponding pair of values of a frequency and the gain at that frequency. And the expression that goes with it is A equals A3 at the frequency omega 3. And because the slope is declining towards higher frequencies, the S must be in the denominator, and the coefficient of the S must be the frequency at which you're evaluating the gain. Because if you substitute S equals J omega 3, the omega 3 cancels, the magnitude of J is 1, and A equals A3, which is the proper answer for the magnitude of the function at the frequency omega 3. And the other case is similar. The only difference is it's a positive slope with increasing frequency, so the S term is in the numerator, and the proper coefficient is that when you substitute S equals J omega 4, the omega 4 cancels, the magnitude of the function is A4 at that frequency. In each case, the phase graph is a fixed minus 90 degrees for the declining slope, plus 90 degrees for the rising slope. Here's a few more for you to play with for a minute or two. Write the factored pole zero forms. The first two are very easy. The third one is a little trickier. Let's look at the first one. One flat gain. take that as reference, A equals A1, look up and down in frequency. If you look down in frequency, there's a concave downwards corner, so that's an inverted pole at omega 1. Look up in frequency, concave downwards corner, that's a normal pole, 1 plus S over omega 2, no zeros. Second one, A equals A1, flat gain as reference, look up and down. Look down, you see a concave upwards corner, so that's an inverted zero at omega 1. Look up in frequency, concave downwards, that's a normal pole at omega 2. Third one, no flat gain. But there's an identified reference gain at a certain frequency, omega 1. The tricky thing is it's on two asymptotes. But that's an advantage because you can identify it on either one of them at your choice to choose for the original reference. Probably the simplest choice is to identify it on the left-hand asymptote, since that's the first one. So, forgetting the second asymptote for the moment, the first asymptote can be identified as A equals A1 at the frequency omega 1, but it's already on the slope. So the S term is in the denominator because it's a negative slope, and the reference frequency is omega 1 in the numerator. So the equation that I've written so far identifies the left-hand asymptote. And from there, it's nothing new. Because now we've identified the left-hand asymptote, and all you do is look up in frequency. Nothing happens going down. If you look up in frequency, you see a normal pole at omega 1. It just happens to be the same frequency we already used as reference. And finally, a concave upwards corner, which is a normal zero at omega 2. So that's one version of the result. But as I said, you have a choice. We could have identified the A1 originally on the middle slope, in which case the first thing you write is A equals A1 at the frequency omega 1, so S will be in the denominator and omega 1 will be in the numerator. But this time, if we identify it with the middle slope, it's a double slope, minus 40 dB per decade, which means you have to square that term. Remember, it's double log scales. Now, the middle asymptote has been adopted as reference, so now you look both down and up and see what happens. And when you look down, you see a concave downwards corner, which is a pole, but it's an inverted pole at omega 1. And when you look up, you see again a normal zero at omega 2. So now we have two versions. Of course, they have to be the same. And it's easy to see algebraically how you get from one to the other. If you pulled out omega 1 over S from this denominator, that would put the pole back to normal form, and it cancels the square on that term. So it's easy to see that they are equivalent. The important thing is you have the choice. And which one you would choose depends on what is the most important part of the graph. It may be that the middle part happens to be important for your design, and you need to keep the other two corners sufficiently far away in both directions. In which case the second version would be the preferable one, because the corresponding formula expresses the part of the graph which is of interest or which has to meet a certain specification. And then the rest of it says how it deviates from that. Well, there's some practice in the relationship between the graph and the formulas, with emphasis on starting with the graph, how do you write the factored pole zero forms? What we have up here is the basis of things we're talking about. This is one typical iteration loop from the trade-off between accuracy versus simplicity. And we're talking about some of the techniques that can be used to simplify and shorten many of these processes. We've talked about low entropy expressions to give more than one piece of information. We've shown how to get low entropy expressions from the start without letting it get out of hand first, by techniques such as doing the algebra on the circuit diagram. We haven't done it in detail yet about how to do it on the graph. And we're now talking about using inverted poles and zeros. And the last thing we did yesterday was introduce those symmetrical representations of the inverted pole and zero. And you had a few exercises in the relationship between asymptote construction and the factored pole zero form of the expressions. Going on to the next topic, we're going to look now at a particular combination of a pole and a zero. This is similar to the simpler circuit we had previously, except now we have a third resistor in series with the capacitor that was previously in parallel with the R2. Again, the objective is to find the voltage transfer function, V2 over V1, and also, again, the simplest way to arrive at that result is to use Thevenin's theorem to get rid of one of the loops of the circuit. So we absorb the R1 and the R2 into the Thevenin equivalent, which reduces it to a single loop circuit, and we can then write the answer in one line as a voltage divider. So the bottom branch of the divider is 1 over SC plus R3, and the denominator is the same thing plus the top branch, which is R1 parallel R2. And the resistive divider is already explicit as part of the Thevenin equivalent, which comes out as a factor in front. One line of algebra then puts it directly into the factored pole zero form, and we see we have a pole in the denominator at omega 1, defined by the capacitance with this combination of resistances, which again is a series parallel combination. Remember not to multiply it all out. And the zero is the same capacitor together with R3. And again, having put it in that form, identify the salient features, which are the flat gain A1, which corresponds to the zero frequency gain, because if you let S go to 0, A goes to A1. And then, starting with the A1 as reference gain, at higher frequencies the pole and the zero will modify that result. So the next thing we want to look at is the sketch for magnitude and phase versus frequency that this network has. So starting from A1, the reference gain at zero frequency, as we go up in frequency we'll encounter either the pole or the zero, depending on whichever comes first. When you look at the expressions for the pole and the zero, you can immediately tell that the pole will come in first. That is, the pole is always a lower frequency than the zero, which is obvious immediately from this low entropy expression, because you see that the capacitor is the same in both cases, and the resistance going with the omega 1 is always larger than the resistance going with the omega 2. So the pole is always lower. To point out the value of low entropy expressions, let me point out that if we did not have this expression in low entropy form, I'll push that up to the top of the picture. If we wrote omega 1 looking like this, that is, we multiplied out this combination, the result would look like this. Parallel combination of R1 and R2 would be product over sum, and then you cross multiply, and you'd get R1, R3 plus R1, R2 plus R2, R3, and in the numerator we would have R1 plus R2. So if you look at that and compare it with the omega 2, it is no longer obvious which one is lower. So there's another very simple example of the value of keeping the results in low entropy form, or in this particular case, deriving it in low entropy form automatically, and it's simply a matter of not multiplying it out into a big mess. It's always the objective, of course, is to avoid the big mess. So in this particular case now, the pole will come first, so we'll have a concave downwards corner at omega 1 with a corresponding minus 45 per decade phase asymptote centered on the omega 1. Eventually, we'll arrive at the omega 2, which is the 0, so it will be a concave upwards corner and a corresponding plus 45 degree per decade phase asymptote. So that's the basic magnitude and phase configuration. Now notice that we have two flat gains, and I've labeled the other one A2, but that was the last thing that happened because A2 isn't anywhere in this formula. But suppose we didn't start with a network, suppose we started with the diagram, the asymptote graph, and we labeled this flat gain as A1, we labeled the other one as A2, and then I asked you, as we did earlier, to write the factored pole 0 form starting from the asymptote diagram. And you see you have two choices. You can either start with A1 as the reference gain, in which case you would write A equals A1, and then you'd look up in frequency and observe first the pole and then the 0, and you would come up with this expression that we started with. But you could equally well start at the other end. You could write A equals A2, and then looking down in frequency, you would encounter an inverted 0 at omega 2 followed by an inverted pole at omega 1. And the result of doing that would be you would get either the expression we started with this time, or you would get this expression. And obviously they're the same thing, and algebraically they must be equivalent as well, so you can get from one to the other, which is easy to do, as you see lower down in the picture. If we start with the original expression we had this time, the interpretation of the A1 is it is the gain as frequency goes to 0. And algebraically, we can pull out S over omega 1 from the denominator, S over omega 2 from the numerator. The S's cancel, collect the terms together, and you get a new coefficient in front, and the pole and the 0 have now become inverted. And if you compare this algebraic result with the one that you would get by writing the same result by looking at the diagram, you see that there has to be an equivalence between these two flat gain coefficients. They have to be the same, which immediately gives you a relationship between the two flat gains in terms of the ratio of the two corner frequencies, omega 1 and omega 2. So the interpretation of this coefficient must be the gain as S goes to infinity, which is the definition of the A2. So rewriting that expression in a symmetric form, what this says is the ratio of the two flat gains is equal to the ratio of the two corner frequencies that separate them. In terms of the picture, the ratio of A2 to A1 is equal to the ratio omega 1 to omega 2. It's sort of a gain bandwidth trade-off. Now, that's actually pretty obvious, because this slope, after all, is 1 for 1. It's simply a reciprocal function of frequency. That was its origin. which we already did. So it follows directly from that even, that the ratio of the two flat gains is the same as the ratio of the corner frequencies. But it's a very simple thing and very useful. And you notice that we now have a choice as to how we represent the function which has that particular graph. We can either represent it with the A1 as the coefficient in front and a normal pole and 0, or we can represent it with the A2 coefficient in front and an inverted pole and 0. They're both the same, they're both correct, and again, it's simply a matter of emphasizing you have the choice, and you use whichever one is most appropriate for the particular application, which means you choose whichever one exposes the gain which is more important. If it's the zero frequency gain that is important in your specification, and you're concerned simply with how the gain deviates from that as you go to higher frequencies, then you would like to have a formula which has A1 in the prime position, the reference gain in front of the whole expression. And correspondingly, if in a different application it's the high frequency gain that is most important and you're concerned only about how it deviates below that, then you'd use the other version. Why not put the important quantity in the prime position in the expression? That's sort of a little refinement to do with low entropy expressions. The main thing is to remember you have the choice. In this particular case, it's easy to check that that expression is correct, that ratio expression is correct, because the A1 is the original resistive divider, and if you substitute for the definitions of the two corner frequencies, you get this ratio, the capacitors cancel, and what you're left behind with is the product of two ratios, representing now the infinite frequency gain, and it's obvious that that fits with the picture, because at infinite frequency the capacitor will be a short circuit, and you'll have, multiplying the original reference gain, you will have a second divider ratio simply of R3 over R3 plus R1 parallel R2, which is exactly what this tells you. So that's the useful result from that expression. Ratio of flat gains is equal to ratio of corner frequencies if you have a single slope. Now, the picture that I drew to begin with shows no interaction between these two corner frequencies. That is, the phase asymptote from the pole is all finished before the phase asymptote from the zero begins. That's only true, of course, if the numerical values are such that 1/10 of the zero is bigger than 10 times the pole. But that may not be the case. And then you get an overlap. And that means that drawing a new picture. And in the case of an overlap, you'd have something that looks like this. And this is a very common circuit. It's called a lag lead circuit for obvious reasons. You get a phase lag followed by a phase lead, and the significant feature is that you get zero net phase change from zero to infinite frequency. You start at zero, you end at zero. The gain, however, has dropped off from one flat value to another. This is the reason why this is a common circuit. It's very frequently used as a compensating network in a feedback amplifier. In a feedback amplifier, looking ahead for a bit, but you know it already, ensuring stability involves meeting the Nyquist stability criterion, which in its simplest form means that you have to prevent the phase lag from getting to 180 degrees while the magnitude of the loop gain is still greater than 1. Otherwise, negative feedback turns to positive with a gain greater than 1, and then you have an oscillation. So basically, the stability criterion is to prevent the phase lag from rising to the point of instability. The lag lead network is a very convenient way of doing that, because you see it has just the property you need. You get to throw away gain and you've got to throw it away somewhere because it's going to go to zero at infinite frequency by itself if you don't help it. But at the same time, you don't want to stack up any additional phase lag, which would impair stability. So this network is often included for that purpose. And in that application, the most useful thing to know about the network is that it's not free. You do get some phase lag, but only temporarily until you get beyond the second corner. So an important thing to know about this network is what is the maximum phase lag you get as a function of how much gain you need to throw away. So that enables you to set up a very simple little isolated problem. Since the gain ratio is equal to the corner frequency ratio, let's simply define that ratio as a parameter k, which shows up in both ratios there. So consider k as a parameter. Keep A1 and omega 1 fixed, and then varying k will vary the position and the corner frequency of the second corner. As a function of that parameter, what is the maximum phase lag you get? That's a very simple little problem because the phase asymptote for the pole remains fixed if the pole remains fixed, and it starts at 1/10 of the pole frequency. And the maximum lag is simply the value of the phase of the pole at the frequency where the overlap begins, which is 1/10 of the zero frequency. So remembering that this is a semi-log scale, minus 45 degree per decade of frequency, evaluating the phase lag at the frequency 0.1 omega 2 is simply the slope, minus 45 degrees, times the log of the ratio of the 1/10 of the zero to 1/10 of the pole. And the 0.1s cancel out, and the ratio of the corner frequencies is the parameter k, which is the same as the gain ratio that we're trying to throw away. So you get this very simple result that the maximum phase lag of the lag-lead network is this function of k, which is the ratio of gains you want to throw away. As an example, suppose you want to throw away 26 dB. 26 dB is a factor of 10 times a factor of 2, so it's a factor of 20. So k is 20. Log of 20 is 1.3. So 1.3 times 45 degrees is the maximum phase lag you would get for throwing away 26 dB. So that's a very simple little result to keep in your notebook. It's sort of like a handbook page, something it's easy to look up when you happen to need that result. Well, we've talked a little bit now about normal and inverted poles and zeros. What do you think about them? Do you like them? Well, you've survived all this time without them, so obviously they're not necessary. But like a lot of these techniques, it's simply something that broadens your bag of tools. You've got more to work with. But I've shown some examples of why I think they're useful. Let me drive that home a little harder now by showing a relationship between the simple expressions you get with inverted poles and zeros versus the more messy ones that you get if you don't choose to use inverted poles and zeros. So consider this example. In fact, this is one that we already had in just examining the relationships that are involved with inverted poles and zeros. What I have recommended is that if you want to write the factored pole zero form for this sketch of the magnitude asymptotes, which has one flat gain, presumably the flat gain is the single most important parameter that you need in the result. So you start the expression by writing A equals AM. That establishes this flat gain as a reference. You look up in frequency, nothing happens. You look down in frequency, and you encounter first the inverted pole at omega A, another one at omega B, and finally the inverted zero at omega C. So this is the format that I've recommended. But suppose you don't want to use inverted poles and zeros. You don't like them. You haven't used them before. You don't want to try them out. And you insist on writing the result in the more conventional format that has normal poles and zeros. Of course, you can do that algebraically. And all you have to do to get it into the more conventional form is pull out front the omega A over S, and the same thing with the other two. Then cancel some terms in front and collect together what's left over, which gives you this coefficient. And what is left behind now is normal poles and zeros. Nice and familiar. And since we have a more complex coefficient in front now, we can lump all that into a single coefficient. And you notice that the nature of that coefficient is that it's a frequency and not a gain, because we've got to keep the right dimensions in this. So we have an S over omega x in front, where omega x is this combination of quantities. So this would be considered a more conventional format for the result in this particular example. And you would describe it as having a zero at zero frequency, and then a zero at omega C, and then two poles at omega A and omega B. And that's fine. This is correct. However, the question I bring up at this point is, where is omega x on the graph? It isn't there explicitly, but it must be possible to locate it somewhere. So where do you think it is? Well, to give you a hint as how to find it, it's the leading coefficient in this expression, so how could you make the rest of it go to 1? So you can expose only the first term. The rest of it would go to 1 if you made the frequency lower than any of these three corners. So S over omega x must be the zero frequency asymptote. So what that would mean on the picture is you'd let S be so low that it would be even lower than the omega C, and all that's left is this asymptote. Not very straight on the TV, is it? Not on this one, anyway. S over omega x must be what I've identified. So now where is omega x? Remember the special case we've had already, where there was no flat gain and we identified a single slope asymptote by identifying the gain at a specific frequency. This is a special case of that. What? Right. Omega x is the frequency where the zero frequency asymptote crosses 0 dB, or unity gain magnitude. So I could draw it like that. Now, without knowing numbers, I don't know where to put that line. It could be up here, could be down there, but wherever it is, omega x is the frequency where the zero frequency asymptote crosses the 0 dB axis. Well, that's okay, but who cares? It's not an important or useful parameter of the problem. So this is an example now again where you have a choice of different low entropy forms. And so why not choose the one which is most directly related to the important parameters of the particular problem that you're dealing with? Obviously, in this case, AM is the most important quantity. So put it out front in the expression. Don't hide it buried in some other parameter like omega x that you don't care about. Now, in order to put the AM in front, you have to use the inverted pole zero format. But that's what it's for. That's really the purpose of introducing the inverted poles and zeros. It just enables you to get the most interesting and the most useful parameters in the result that you're dealing with. Remembering again, you need all the help you can get to do a design problem where you have to work with insufficient information. So at least maximize the information you do have. This is one of the ways to do that. Okay, so there's nothing wrong with using only normal poles and zeros. It's just that it may not be the most useful thing to do. Now, even this format that I've labeled conventional is still not universal. A lot of people would multiply out another further step and write this as S plus omega A, S plus omega B, and so on. In fact, you might even say that's more conventional. And, of course, algebraically, you can do that too. Look at this example, also one of the ones we had earlier. This is the one I recommended, where you write directly from looking at the asymptote graph, A equals AM, and then two normal poles followed by a normal zero. But now suppose you don't like even this format, which is sort of using normalized frequency. Suppose you want it in the format on the right. That's easy to get. And once again, all you have to do is bring out some terms in front, collect them together, and define a new parameter. That parameter, once again, is a frequency and not a gain. And you have to realize that even to get the right sort of symbol. The coefficient in front must be a frequency in order that the dimensions of the whole expression come out right. So this is also a correct result, and maybe even more conventional than before. I suspect the reason that this is perhaps the most popular result is that when you look up tables of Laplace transforms, this is the format that they're usually given in. But that's not a very good reason for using this format, because again, I ask you the same question. There's a new parameter in here, omega y, and where is it on the graph? Well, this should be a lot easier this time. Now you know how to go about it. Follow the same procedure. What do you have to do to make the other factors in the expression go to 1 so that you expose the omega y coefficient in front? This time it's the other direction. To make this factor independent of the three corners, you have to let s go to infinity. That leaves you with a 1 over s, which is why the coefficient in front is a frequency. So the infinite frequency asymptote, this one, is omega y over s, where the rest of the term has gone to 1 at infinite frequency. And so directly from that, omega y is the frequency where the infinite frequency asymptote crosses 0 dB. So there's one possibility. And again, I don't know where to draw that line without knowing numbers. It may be at any vertical position, but wherever it is, omega y is the frequency where that final asymptote crosses 0 dB. So it's the same result as before, except at the other end of the frequency scale, and the same conclusions apply. This conventional result is correct, but why obscure the important quantity, which again is AM? Why obscure that in favor of some other quantity which you don't even care about? Turning this argument around for a moment, from the project manager's point of view rather than the design engineer. This is going back to a point I mentioned at the beginning, which is you're going to review reports by your design engineers, or maybe the design review committee is going to review these reports. People who look at a report need to see the format in a way in which you can tell immediately what the shape of the graph looks like, or the other way around. And you have, if you have it in the format that shows the important quantities out front, as a reader you see immediately, yes, that's right. But if you get it in a more obscure form, which is not as low entropy for this purpose, you don't know whether it's right or not. You simply have to rely on the designer who did it and hope that he didn't make a mistake. So that's another value of having low entropy expressions, where you make a conscious effort to expose the quantities which are relevant and important for the particular application. You may think I'm overdoing this by emphasizing it so much, but it is such a simple thing to do, but you just have to get in the habit of doing that. It's like editing a manuscript. It comes out pretty much right the first time, maybe, but you have to go back and clean up and edit and reword some things in order to make sure that you are transmitting exactly the information and the viewpoint that you intend to, and that your point isn't lost somewhere or buried, which means the reader either skims right over it and never notice it, or he has to go and dig it out for himself. And of course, no one's going to take the time to do that. Okay, so conclusion of that particular topic is, if you have more than one flat gain, you have a choice of which one to set out front as the reference. And you notice a trend here, because obviously you can extend this to any number of flat gains. Whatever flat gain you choose as a reference, corner frequencies that are above that gain will show up in normal format. Corner frequencies that are below it will show up in inverted format. And here's a little more complicated case just to illustrate that. There are three flat gains. I've already written on the picture necessary relationships between them, employing the gain bandwidth trade-off ratio. And here are three different versions of how to write the factored pole zero form, choosing each of the flat gains in succession as the reference. And chose red also just to illustrate more clearly the difference between whether the corner frequencies are inverted or normal. So you see those below the chosen reference gain are inverted, those above it are normal. So now you have the full symmetry of the two directions of frequency, and it's useful to get equally adept in writing the result in any form or any combination in order to expose the most useful things. Well, here's something else that you can practice on your own. Three sets of asymptotes, which obviously are all the same. The only difference is I've identified reference gains in three different places. on the supposition that the context of the problem is that in each of these cases, one of these gains is more important than the other one. And you can practice again just to get familiarity with manipulating these things by writing the factored pole zero form for the asymptote structure, choosing each of these reference gains to put out front of the expression. There's nothing new in there that we haven't done already. Okay, we've talked about asymptote structures now for voltage gains. Obviously, exactly the same thing would apply to current gains, both dimensionless quantities anyway. But you can extend the application to quantities that do have dimensions, such as impedance and admittance. There's only one additional feature required in that case. Here's an expression for an impedance. Let's not worry about what circuit it comes from. It's in factored pole zero form. And two of them are normal, one of them is inverted. And the only extension needed from the previous notation is that the coefficient in front now has the dimensions of a resistance, sort of the scale factor. So Rm now has the significance of a flat resistance. And looking up in frequency from the reference value of the resistance, we encounter a normal pole at omega 1 followed by a normal 0 at omega 2. And if you look downwards, you encounter an inverted pole at omega 3. Now, what sort of scale should we choose for this? Remembering that this is a logarithmic scale, or at least we'd like to keep it logarithmic. There's no point in changing the structure of the diagram just because we're talking about an impedance instead of a voltage gain. And we can still use exactly the same asymptote structure, remembering also that the smooth corners go along with it as well. The actual curve for the magnitude of the impedance versus frequency, of course, has smooth corners just as the voltage gain did. 3 dB down points and 1 dB points and so on. The only difference is that since we're going to use a logarithmic scale, we can only take the log of a dimensionless number, which means that we have to choose a normalizing resistance. And you can choose any value you like. I just called it R. So what you do is that you divide both sides of this expression by the same normalizing resistance, R. And that makes this coefficient dimensionless again, just like a voltage gain. Then you can convert it to dB by taking the log and multiplying the log by 20. So the reference resistance that you have chosen then corresponds to the 0 dB level, because 0 dB means a ratio of 1. So when you have 0 dB for the magnitude of the impedance, what you're really saying is the magnitude of the impedance is equal to the reference resistance when the ratio is 0 dB. So you can have a dB scale on the left, or you can have a true logarithmic scale of resistance on the right, and the reference resistance that you've chosen sets the 0 dB level. And you can simply scale that up and down as you wish by choosing different values of reference resistance. Now, the only catch to this is when you label the dB axis, you ought to label also what the reference resistance is. Otherwise, you don't know what 0 dB corresponds to. Unfortunately, a lot of people don't bother doing that. They just write a 0 dB scale for impedance. And if you don't say what it is, the implication is the reference resistance is 1 ohm. Maybe it's 1K. But you don't know unless whoever drew it specifies what units you're using. So to be strict about it, you should always use or specify what the reference value of resistance actually is. The phase graph, of course, is completely unaltered because that's independent of what the coefficient in front is anyway. That's only a property of the poles and zeros. So in this particular example, the inverted pole has a negative phase slope, minus 45 per decade, centered on the pole. And then a normal pole also has a minus 45 per decade. And the zero will bring it back to 0 degrees again eventually. I drew the case where there's a substantial overlap, but it may not, depending, of course, on the relative values of those two corner frequencies. Here's some examples you can play with on your own also, just to see what happens with resistance. Here's an example I'll go through first. Another simple network. The objective this time is to find the input and output impedance in factored pole zero form. The input impedance is just the sum of R1 plus the other two in parallel. Remember, we've already seen that a resistance and a capacitor in parallel has an impedance which is equal to the resistor with a single pole corresponding to the time constant of the C and the R. One line of algebra to cross multiply gives you the factored pole zero form. In the normal pole zero form, the coefficient in front, R1 plus R2, of course, corresponds to the zero frequency value of the input impedance. But because we have a pole and a zero, it's just like the lag-lead network, so you have an alternative form. You could use the infinite frequency impedance as the coefficient in front with an inverted pole and zero. Algebraically, it's easy to get from one to the other. Here's the sketch that goes with it. Using the normal pole zero form, the reference value is R1 plus R2 at zero frequency. As frequency goes up, you get to the pole or the zero, whichever comes first. Looking at the expressions for the pole and the zero, obviously the pole must be lower. Again, because of the low entropy format, where you still retain the parallel combination in the expression for the zero, you know that the parallel combination is a result which is smaller than either of the two parallel elements, one of which is R2, which is the resistance that determines the pole. Therefore, the zero must always be a higher frequency than the pole. So the sketch will always have this shape. And it will end up, of course, at R1, corresponding to the infinite frequency value, which you would get from the inverted pole zero form if you let S go to infinity. So that's the input impedance. Output impedance, you do the same way. Look in at the definition of output impedance is you look in at the output while you make the input signal zero. In this case, the input signal was a voltage, so when you make it zero, you essentially short the voltage source. So when you look in at the output, you're going to see the capacitor in parallel with the two resistors in parallel. So immediately the result is a triple parallel combination, and you keep the two resistors in parallel together as a single element, and the answer is the same as before. It's a parallel capacitor and a combined resistor, so the impedance is the effective resistor with a single pole at a frequency corresponding to the CR product. The sketch that goes with that, magnitude sketch, at zero frequency, the output impedance is R1 parallel R2, which must be smaller than R1, which must be smaller than R1 plus R2. So you know what the relative positions are of these asymptotes. And in addition, the pole of the output impedance is the same frequency as the zero of the input impedance. So you know all about the relative positions of those two sketches. Now, here's a couple that you can try on your own, even simpler as a matter of fact. Find the factored pole zero forms for input and output impedances and sketch the asymptotes for those two pictures. Well, we're going to go on now to another example, a little more complicated this time. a circuit now that has two capacitors and a few resistors, and I've specified the particular problem of interest right now, which is finding out the voltage transfer function V2 over V1, and I've written it in the format that employs the kind of wording that I recommend, which is analyze the circuit for the response V2 over V1 using the given values to justify appropriate analytic approximations, and express the result in standard factored pole zero form, which I've specified here. The capital Pi, of course, simply means product of any number of zeros, product of any number of poles. And the reason I specified it that way is that this is exactly the problem that I give my class at Caltech at the very beginning of the year, before I've talked about any of these shortcuts or low entropy expressions or anything. It's their first homework problem right off the bat, and I tell them, I'm giving you this problem because I just want to see what you're going to do with it. Based on what you already know, I want to see how you approach the solution. So the capital Pi is simply so that I can avoid telling them how many poles and zeros there are supposed to be in the circuit. Sketch magnitude and phase of the gain showing the straight line asymptotes. Label salient features. Salient features are the flat gains and the corner frequencies, with both the analytic expressions, which we now know, of course, ought to be in low entropy form, but they haven't heard that yet, and corresponding numerical values. Okay, so what happens is, a week later, they show up, turn in the problems, which are usually multiple pages, and the starting point is a huge equation, which you get by treating this as a giant impedance divider, where the bottom branch is all these three branches in parallel, which is what all this mess is on the top. This is the parallel combination of those three branches, and the denominator is the same thing all over again, plus the series branch, which is R1. So then they do a lot of algebra, getting the result into the conventional format, which is the ratio of polynomials in complex frequency. This is a high entropy expression because everything's all multiplied out. And you can't see anything useful to get out of the answer, although some of them may take the next step, which is to make each of the polynomials in S have a leading term of 1. And the way you get that, of course, is you pull out R1 plus RL from the denominator, which means you have to divide it into the second and the third coefficients. And then, if you gaze at this combination long enough, you can determine that it's this series parallel combination. And the same combination shows up in the other two terms as well. So by putting mental energy into it, you can lower the entropy. However, that's more work than necessary. You could get the same result in low entropy form by starting with doing some of the algebra on the diagram. And the key is the same as the one that we've done lots of times already, which is use the Thevenin reduction to get rid of one loop of the circuit. This resistor RL could just as well be on the left of the other two branches. It wouldn't change anything, except it's a little more obscure to recognize it when the possibility when it's out here. But if you simply move the RL to the other side, R1 and RL can immediately be absorbed into a Thevenin equivalent, and you're left with only two parallel branches instead of three. Incidentally, the RS is a red herring. RS has nothing to do with the result for V2 over V1. That wipes out a few of them right away, of course. Yeah. Anyway, using Thevenin reduction now gets you to this simpler circuit. And now you have a smaller equation to begin with and considerably less algebra. But the main bonus is the answer automatically comes out into the low entropy form, in which, of course, the R1 and the RL are in parallel to begin with. That was the benefit of making the Thevenin reduction. So you don't have to recognize that at the end and restore it. Okay, that's the first phase of the solution now. And you may recognize this as the exact equation we already had in the introduction, where I was summarizing these points, when I was mentioning the possibility of using numerical values to justify analytic approximations. And when you look at this middle coefficient, the coefficient of the S term, it's the sum of two components, one of them with a C1 and the other with the C2. And when you look at the tentative set of values, you see that the C1 is 50 times bigger than C2. And associated with the C1 is a resistance which is bigger than the resistance associated with C2. So both of those effects go in the same direction to make the C1 term even more than 50 times bigger than the C2 term. So there is less than a 2% error in neglecting the C2 term. And you can see all that without actually going through the substitution of any numbers, because you can do that in your head easily enough. The next step is where we have the deviation from the usual procedure, which is, having used the tentative numerical values to justify dumping the C2 term, you leave the rest of it in terms of symbols. And now we'll continue with the solution in terms of symbols, so we still have a general result, and that will give us the opportunity to change the numerical values at the end if we need to modify the numbers in order to meet certain specifications. And, of course, according to the mathematicians, we're going out on a limb by doing that, because we still would need to go back and check that the term we left out is still negligible even after we've changed the numbers. But as I've emphasized often enough now, you can't lose by trying it in the first place, because you can never be worse off than if you hadn't made the try. So in this particular case, let's go ahead and dump this term, even if we are going to change numbers later. Okay, the final result now, already you can see from this expression, is that we have a flat gain coefficient in front, and we have a linear function of s in the numerator that immediately defines a 0, and we have a quadratic function of s in the denominator, which means we will get two poles. So I've designated them omega 1 and omega 3. All of them are in normal format, which means the coefficient in front is identified as the zero frequency flat gain asymptote. So the next thing is, what are the two poles, which of course are the solution of this quadratic equation. Even with the simplification, it remains a quadratic. And so now you wheel out your familiar formula for the solution of a quadratic. And here it is, with substitution for the ABC coefficients in terms of the circuit elements that already exist, and you can immediately see where that comes from. And this is the other point that I emphasized in the introduction, which is, this is a high entropy expression, and you might as well not have bothered to write those symbols in there because they're worthless. You might as well have put the numbers in right away. And I've written over the expression what the actual numbers are. And the conclusion is, this result is useless for design because you can't work it backwards. knowing what the two corner frequencies are, it's hopeless to try to solve for any element values. But it has another problem as well. It is computationally inaccurate. Because when you look at the value of the C1 term, it's 3.3 times 10 to the minus 3, and here's the same term squared. So that's 10 to the minus 6. From that, you subtract 0.026 times 10 to the minus 6, then take the square root, and then subtract it from the original C1 term, and those two terms are almost equal. So you multiply computational inaccuracy by doing that. So this is by way of a lead-in example to set up the point that the conventional formula for the solution of a quadratic equation is a lousy formula. Now that may be a heresy to say that, because we will never forget that, none of us. It's probably the first formula we ever learn in the first algebra course. So it's deeply ingrained. And I've discovered in talking about this around the world, it looks as though all school kids learn it even with the same coefficients, ABC. So it is really universal. But I'm suggesting it's a lousy formula and you're better off to forget it. And because that probably does sound heretical, I'd like you to find out for yourselves right now why it's lousy. One reason I think is already obvious. That is, if you substitute symbols, it's a waste of time because it doesn't tell you anything. And you've recognized that every time you've used this formula. But you haven't thought that there was anything you could do about it. Well, you can. The other disadvantage, you may not have even recognized. The fact that one of the two roots is computed with much less accuracy than the other one. See, in the case of the numbers that we have here, the root that has the plus sign is no problem. You're adding two almost equal numbers, you don't degrade accuracy. It's only the one where you subtract them that you degrade the accuracy. So that's the part that I'd like to follow up with a more specific example, and in fact a little more extreme one. I should have shown this earlier. This is justifying the leaving out a term for the numerical approximation. Okay, now I've posed the problem that the conventional quadratic formula is no good. So I'm translating this now out of the particular example that led into it, back into the familiar coefficients and the sort of abstract algebra that format in which we all learn it. So here's ax squared plus bx plus c. Let me ask you a question right away to see how much you know about interpreting the results of the quadratic. There are three coefficients in that equation, a, b, c. How many of them determine the roots? Well, the first answer that comes to mind is three of them, because the formula that you all remember has all three coefficients in it. But in fact, that's not true, as you see from the very first line here. Suppose you pull out the a coefficient in front. Leaves you with a pair of ratios, and if you factor that quadratic, these are the two roots that you get, x1 and x2, which are given by the conventional formula, but there are really only two independent parameters, not three, that determine the two roots. The a in this format is actually only a scale factor. You could rewrite the formula in terms of these ratios b over a and c over a. You could do that, but no one ever does. Anyway, that's a very basic point. only two parameters actually determine the roots of the quadratic. Okay, now I'm proposing that this conventional format has two disadvantages, which I've already mentioned. Here's the high entropy problem. Here's the computationally inaccurate one that we just talked about. But I want to expand on that. Take an even simpler example. Take A equals 1, take C equals 1. I've changed the variable to Z instead of X just because this is a separate numerical example. So we're down to one parameter. Let's take B equal to 45,000. The formula, conventional formula, reduces to this version now with A equals 1 and C equals 1. If you have a pocket calculator with you, you might like to go through this yourself right now. Using the calculator and the algorithm in the specified form, just compute what the root Z1 and Z2 are for B equals 45,000. It won't take very long for you to try this out, but if I see someone's doing it, so let's see what number you come up with. Well, on my calculator, which is an HP 15C, I get minus 2, 0, 0, 0, 3 more zeros, 3 more zeros, times 10 to the minus 5. Doesn't matter what Z2 is. We don't have the problem with that one because both signs are the same in this term. Only the Z1 term is the one that has a potential numerical inaccuracy. So you got minus 2.2, I got minus 2.0. That's quite a big difference. So we get a little feeling of unsettledness right now. Let's make a small difference. Let's simply rearrange the formula so we calculate by a different algorithm. Call the first one Z1A, it's called this one Z1B. All I've done is pull out in front minus B over 2. So the rest of it goes into this format. Now there's no approximation. This is exact. But now work out the computation using the second algorithm. See what you get. Well, while you're doing that, I'll write down what I got, which is minus 2.250, then a lot more zeros, times 10 to the minus 5. Minus 2.2275. Okay. Well, now we get really upset. 4 different answers. Which one is right? Even worse, maybe none of them is right. How do we know? We made no approximation. The fact that we got different answers for the two algorithms, even with the same calculator, suggests that the algorithm itself has something to do with this. So let's manipulate the result a little more and see if we can shed any more light on which one may be right. Incidentally, I'll show the two results that I got and also the other one, which isn't of any particular significance. But notice the two results that I get with the same calculator differ by more than 10%. So now let's manipulate that and see whether we can learn anything more about it. Try a third algorithm, successive approximation. Here's the original quadratic. All I've done is move the z squared plus 1 to the other side and substituted for the particular root z1, which is the one we're concentrating on. Divide both sides by b, and this is the result for z1, but the z1 is on the other side as well. But we know that the value of z1 is very much less than 1. Even if we don't know exactly what it is yet, at least we know it's very small compared to 1. So a first approximation to the numerical value of z1 is simply to drop the z1 squared on the other side, knowing that it's much less than 1. So the first approximation to z1 is simply minus 1 over b. Then the second approximation we will get by substituting for the z1 on the right-hand side the first approximate answer, which is 1 over b squared. So the second approximation to z1 is minus 1 over b times 1 plus 1 over b squared, which I can multiply out into two separate terms. Now I get my calculator out again, the same one, and 1 over b is 2.2 recurring. My calculator is a 10-digit calculator, and I've written all of them out there. Then the second approximation is an additive term, which is this number. And you see the first significant figure of the correction term is in the position of the last significant figure of the first approximation. So I now claim that the correct numerical answer for z1 is 2.2 recurring up until the 9th digit, and I can drop the 10th one by neglecting the correction term. So I claim that this is the correct answer to 9 significant figures. That isn't any of the answers we got before. So the purpose of this example is to shake your faith in that formula, at least with this particular numerical value. And in fact, if you look at the error of the first two answers that I got, again, all using the same calculator, the first one was off by more than 10%, the second one was off by 1.25%. The interesting thing about this result is, sort of ironic really, both computations using the exact formula gave wrong answers. We got the correct answer using an approximate formula. Just backwards from what you normally expect. Sort of shakes you a bit, I hope. And yet, my calculator is a 10-digit calculator. And you normally think that for engineering purposes, where anything better than 10%, certainly 1% is good enough, you never think you have any problem using 8, 10, 12-digit calculators. So the purpose of this example is to illustrate that isn't true. You can get quite gross numerical errors, even exceeding 10%, with very simple calculations. And what could be more simple than the old quadratic formula? So the purpose of this is it's a caution. Watch out for multiplication of computational error. Now, as a matter of principle, of course, you're well aware of that. And we even talked about it in the introduction. In relationship to fairly high-powered computers and numerical analysis methods which are set up to deal exactly with this sort of problem. But you tend to think that that sort of problem is sort of esoteric and you don't have to worry about it for ordinary engineering accuracy calculations with your handy, familiar pocket calculator. So this is a caution to indicate that you do have to worry about it. As a matter of fact, obviously the choice of the numerical value of the B coefficient is very significant here. And I purposely chose the value so that with my 10-digit calculator I get these discrepancies. If you have an 8-digit calculator, the answer comes out 0. That's a rather large percentage error. But another interesting thing is, if you look into this in even more detail, even relatively small changes in the value of the B make quite a difference as well. Notice I've computed here Z1A and Z1B. These were the two initial values from the two initial algorithms. For B equals 45,000. This is what happens if you take a sequence of numbers for B. For the two routes according to the first two algorithms. Notice the error isn't even in a single trend. It moves about quite a bit. Sometimes one is better than the other even. Sometimes the other way around. Sometimes you don't get any error. So that's perhaps even more impressive in saying you've got to be careful about numerical algorithms. Well, I hope I've shaken your faith in that high school formula. But of course, if I'm going to demolish it successfully, I'd better suggest something to take its place, which I hope will be more satisfactory. So let's go back to the beginning and see if we can rework the algorithm and come up with a better answer. This is the starting point now, the computational accuracy problem, which we now want to overcome. So I propose this as a better method of expressing the roots of the quadratic. Let's start with the x2. That's the one where we don't have any problem numerically because we have the same sign between the two terms, so we're adding numerically and not subtracting. All I'm going to do with that one is rearrange it a little bit. So I'm pulling minus b over a out front. What is left behind in the square bracket, I'm simply going to call it f for no particular reason. In addition to that, I'm defining another parameter, q, such that q squared is just ac over b squared. That's just a notation change. Nothing strange about that. Now let's work on the other root, which is the one that has the computational problem. Start out the same way. Bring a minus b over a out front, and we're left with a square bracket, which is not the same as the original one, because it has a minus now between the two terms instead of a plus. Now we have a radical sign up in the numerator of this expression. You may remember something else from when you first learned about the quadratic back in high school. You remember a little trick called rationalizing the denominator? What that meant is that if you had a radical sign in the denominator, you could move it into the numerator. Well, I'm going to do the same thing except in reverse, which fits very nicely with the whole philosophy of what we're talking about, where design is the reverse of analysis. You noticed I do a lot of things backwards. So I'm going to rationalize the numerator. I'm going to take this square root up here and I'm going to put it in the denominator. And the trick that you use to do that is you multiply top and bottom of the expression for x1 by another square bracket, which is the same as the one that's there already, except for the opposite sign. So I multiply top and bottom by 1/2 plus 1/2 times the square root. So now I look at the two square brackets in the numerator and multiply them out. And these are of the format a minus b times a plus b, which is a squared minus b squared. And now you see why the radical disappears. And this exposes now the crucial step. Because when you do this multiplying out and the following subtraction, you get 1/4 minus 1/4, which is 0 exactly. And the q squared term is left behind. And you see that the computational problem arises when the q squared is very small in the original result. That's when you get the problem. Now, by this approach, you do the subtraction of the two almost equal numbers analytically before you substitute numbers. That is, before you get out your calculator. So there is no round-off error. The small difference remains exposed exactly. That's the crucial step. Well, what's left? After you substitute back for the q squared in terms of the original coefficients, the answer is minus c over b 1 over f. And so now, when you collect together the two results, these are the two roots of the quadratic equation. Let's keep the f up on the top then. And you see the f is the same function in both places. F has the plus sign. So now, in the last step, you get your calculator out and you substitute the numbers for a, b, and c, and you compute f. And you get an accurate answer for f. You get as accurate an answer as you have digits in your calculator, because f has only the plus sign, and you use the same f in computing both roots. So you get both roots with equal accuracy, as good as the accuracy of your calculator. That's how you overcome the numerical computational accuracy problem of the original quadratic. Now, this is a longer derivation than necessary. But I did it because I wanted to expose the crucial step of why it gives you a better answer. But actually, you can get it much more quickly than that. Start again. Write the conventional expressions for the two roots. The x2 is the good one, so we modify it slightly by bringing the minus b over a out front. The other one is the bad one. So don't use it directly, but instead use another property that you learned at the same time you first heard about the quadratic solution, but you may have forgotten this one. Here's a repeat of the earlier picture. The product of the two roots is equal to the constant coefficient, because if you multiply out this expression, x1 times x2, the answer is c over a. Now we already know one root with sufficient accuracy, which is the x2. So if we already know x2, all we have to do to find x1 is divide x2 into c over a. And that immediately gives the new answer for the x1. So there's the two results we just had, with f explicit in terms of the original coefficients. So that's all there is to it. This is my recommendation for the formula for the roots of a quadratic equation in a form that overcomes the computational accuracy problem for one of them. In other words, you get both of them with equal good computational accuracy. That's not much of a difference, is it? But there's something else that's a bonus that you get with this too. It also solves the other disadvantage of the conventional formula, namely the high entropy problem. Because look at what the format of these results tells you now. Here it is in terms of the f again. There's the definition of the f. Notice that apart from the f, this formula gives each root as a simple ratio of 2 of the coefficients of the original quadratic. Now, wouldn't it be nice if f was 1? When you remember that ABC are complicated combinations of circuit elements, well, what possible values can f have? Here's the definition of f. And you see right away that if the q squared is small enough, f approaches 1. Even more explicitly, if the q is bigger than 0.5, this is the square root of a negative number, and of course you get a complex pair of roots. If q is equal to 0.5, f is equal to 0.5, and you get 2 equal real roots. If q is less than 0.5, f is real, and you get 2 unequal real roots. And the interesting case is if q is much less than 0.5, f approaches 1, and therefore each of the 2 roots becomes a simple ratio of original quadratic coefficients. And here's what a graph of f looks like. If q is bigger than 0.5, you have a complex pair, so you can't draw it. If q equals 0.5, f is 0.5. If q drops well below 0.5, f approaches 1. And the additional information you get by looking at this simple little graph is, look how rapidly f approaches 1 as q drops below 0.5. In fact, if q is even 0.3, f is already 0.9. It's within 10% of its final value of 1, even if q is as big as 0.3. So what that enables you to say is, remember, q of 0.5 or less gives you real roots, as distinct from a complex pair. So what this graph tells you is, whenever you have a quadratic equation that has real roots, it's a darn good approximation to take f equal to 1, and you can express the 2 roots as simple ratios of coefficients without any radical sign. Real roots is half of the number of cases. That may not be a very realistic classification, but if you consider the spectrum of possibilities, real roots is half of the spectrum. And so if in half of the cases you can get rid of the radical sign in the quadratic formula, see how much simpler that makes the analytic results. That's the bonus you get from the alternative version of the formula, in addition to the improved computational accuracy. So this is very simple stuff. And a few people find it out, sort of just by use, a lot of people never find it out. And I've been talking about this for a long time. As I mentioned, all of this stuff began as an evolution of the course that I do at Caltech. So I talked about that for more than 20 years. More recently, I've been talking about it outside, in circumstances like this. Only last year did I stick my neck out far enough to give a seminar at another university, talking about low entropy expressions and using this as a very basic example. And I was really concerned about doing this. And I did it at University of California at Berkeley, which is a pretty high-powered place. And I gave it as a graduate research seminar, which this really isn't, of course, because that's the only forum you can get. And there was a fairly big audience there because they didn't know what they were going to get. And right at the outset, I asked them the same question I did you before I'd said anything about this, and without even giving them a hint about the background of low entropy expressions. I said, how many of the coefficients of the quadratic determine the roots? Only a couple of people knew. One of them was a professor. So then I went through this, and only a bare handful, 2 or 3, had recognized that you had some choices about how you express the results. And none of them had recognized this huge discrepancy in the computational accuracy of the 2 roots. So I was reassured after doing that, and I was very careful to ask around afterwards, did you think this was worth anything? And after I got through the layer of politeness, then people actually said, well, it was useful. Well, that's really all of these things are about. Very elementary stuff. And if you write an abstract of a seminar that you're going to give somewhere, you can't say this. No one's going to come to a seminar to hear about quadratic equation solutions. But, do you agree that this is useful stuff? A lot of the things that we do, we get taught at an elementary level. We usually go over it again, maybe several times, as part of more advanced courses, because you build on it and you get different insights into it, and as you mature and you're thinking, you get different perspectives. But somehow no one bothers to tell you about this. And as I say, a few people find it out, but not many. And that's really true of most of these techniques that I'm talking about for these few days. There's not much of it that you really didn't know already, but it was buried somewhere. Or you hadn't recognized a different format that would be more useful. So that's really all these words to do with low entropy are about. I said this course at Caltech evolved over many years. And most of these techniques I've been talking about for many years. But the term low entropy I only introduced a couple of years ago, because I found that my original expectation when I was doing the course, which was applied to analog circuits, I used these shortcuts and tricks. I didn't use those words. I just used the methods. When I was deriving something or going through some circuit analysis, and I kind of expected that the students would get the idea about these techniques sort of by osmosis. that if I used this technique, they would too. It didn't work very well. Very few of them did that. Most of them simply went on and did the homework problems using the same techniques they had before. It's natural because that's what you're used to. But I decided this wasn't good enough, that I wasn't getting the point across about the techniques, and so I decided that what I needed to do was simply give names to them. And that's why I came up with low entropy expressions. I'd always emphasized arranging the equation and grouping the terms so you could see what was going on, but they didn't do it. So now when I said this is a low entropy expression, then they have a goal. They have a definition. And so now I've incorporated it all the way through, and I keep referring to it more and more. But it's really overexposure. But I think you have to overdo things and exaggerate things in order to overcome years and years of ingrained methods that actually may not be optimum. So that's why I keep putting these interpretations on this stuff as we go through it. Okay, back to the original quadratic. Pull out the a in front, define x1 and x2 as the roots, and here is the substitution of the roots according to the new version that I've just introduced, with no approximation. This is exact as long as you retain the f as being non-unity. But the benefit, the bonus is, if the q is small enough, then you can take f approximately equal to 1, and then the roots reduce to simple ratios of the quadratic coefficients. Now, that completes one line of derivation based on the conventional quadratic formula ax squared plus bx plus c. But let's talk about a slightly different version, which is consistent with the way I've been writing frequency functions all the time up to now. You may have noticed that my polynomials in complex frequency S have been in reversed order. I start with the 1 in front, then the S term, then the S squared, and so on. Not that there's any difference. It's simply, once again, that I tend to think of rising frequency as going from left to right in the standard diagrams. So why not make the relevant terms go left to right as well? A very small point and not really important at all. But I just happen to prefer that because I like rising frequency to mean you go further to the right in the equation as well as in the graph. So that's why I write my polynomials in the other direction. So suppose I do the same thing with the quadratic. Now the leading term is not a but c. So I bring the c out front, and the consequence is that the roots x1 and x2 are now divided into the x term instead of being added. Just like we have in frequency response, where the x1 and x2 now become omega 1 and omega 2, which are the corner frequencies directly. And that's what we're interested in. Well, the formula for the x1 and x2 remains exactly the same in terms of the f and the q squared as before. And here's the direct substitution into the factors of the quadratic. And again, which is picking up the point that was brought up earlier, there are only two independent parameters that determine the roots. So you can rewrite them as a1 and a2. So if I redefine them, as I have down here, here's the quadratic with ascending powers of x, or complex frequency, with appropriate coefficients in terms of circuit elements. Here are the factored format in terms of two corner frequencies, and this is what they are in terms of the A1 and A2 parameters instead of the original ABC. Simply an alternative format. And here's the limiting case. If you have real roots, then f is approximately 1, and you can factor the quadratic very simply. Here are the two factors, and in the alternative notation with the a1 and a2, again, here are the two factors. No radical sign. So that's an alternative format, and here's a summary of it. The left-hand column is the conventional ABC coefficients. The right-hand column is the A1 and A2 notation. F function is the same in both cases, and the Q squared is this in terms of the ABC, and it's this in terms of the A1 and A2. Here are the exact roots, both cases, which factors the quadratic into these two formats. And the limiting case for real roots with Q small enough, f is approximately 1. F drops out, and the radical goes with it, and you're left with these simple ratios of coefficients for the two roots. Notice particularly the one with the A1 and A2, because it's easy to remember this and use it all the time. Whenever you have a quadratic equation in this format, if the roots are real and well separated means the Q is a long way below 0.5, the quadratic approximately factors into these two simple terms. And notice the first factor is identical to the first two terms of the original quadratic. And the second factor is found as the ratio of the third to the second coefficient. So, to summarize this, the advantages of this version over the conventional formula are twofold. It overcomes both of the disadvantages. You can compute both roots with equal accuracy because you avoid the small difference of large numbers. And for real roots, to a very good approximation, the radical disappears. Each root is a simple ratio of coefficients of the original quadratic. So here's the way to approach finding out which case is relevant in your particular problem. Whenever you find a quadratic, the first thing to do is to find the value of its Q factor, which you can do directly in terms of the known coefficients. If Q is bigger than 0.5, you know you have a complex pair, and you should leave the result in the quadratic format, which we haven't talked about yet, but we're going to shortly, to do with RLC filters. What you do is you define a normalizing frequency, and there's one parameter left, which is the Q factor. On the other hand, if when you determine the Q from the original coefficients, it's less than 0.5, a good approximation is to take f equal to 1, in which case you factor the quadratic into two approximate real roots, which are very simple. That's the end of the diversion to do with properties of the quadratic. Now we go back to where it came from, which was that low-pass filter network with two capacitors that gave rise to a quadratic equation. And here it is again. This is the denominator of that voltage transfer function for the network that we already looked at. After dropping out the second part of the middle coefficient, using the numerical values to justify analytic approximations. Now, I didn't finish the story about what happens when I give this same problem to my class at the beginning of the whole school year. Of course, when they get to the quadratic, they substitute the R's, all the circuit elements into the huge formula, and then they put numbers in, and they come up with a whole spectrum of numerical values for one of the corner frequencies, including 0. Turns out one of the poles is 0 if they use an 8-digit calculator. That doesn't bother them. Even when they sketch the asymptote results, and because the pole goes to 0, the gain goes to infinity at 0 frequency. That doesn't bother them. In spite of the fact that it's a passive network. So anyway, they find out that way that they get a lot of inaccurate answers for one of the roots. So then later on in the first term, we've gone through all this stuff about quadratics and low entropy and so on. Then you get the same problem again. And at this time, most of them use the improved version of the quadratic formula, which brings us back to the point where we are here right now. This is the denominator that needs to be factored into the two roots. These are the initial numerical values. So the approach from now on is these coefficients represent the A1 and the A2 in the version that we've just had. So the first thing you do is find out what the value of the Q is. So here's the definition of Q. Q squared is A2 over A1 squared, which you get this. And you can in fact reduce it very simply, although you don't even have to go that far. And you see immediately that because C1 is 50 times bigger than C2, and R1 parallel RL is a lot bigger than R2, then Q squared is indeed very small, and Q is much less than 0.5. Very much less. So to a very good approximation, F is equal to 1, so you can use the real root result, which is one of the roots is simply 1 over A1, and the other root is A1 over A2. And when you make that substitution, the A1 is already explicit, and it gives you directly a corner frequency. The other result is immediately reducible because the C1 cancels, and you're left with sum over product, which is 1 over parallel combination, in which one of the components is already a parallel combination. So you end up with a triple parallel combination. The parallel combination is slightly more obscure in this case, but still you should practice looking for it and recognizing the result when it's there. So these are the two analytic results now, and here's the substitution of numerical values. Another little trick that I'm sure you've all discovered long ago. When you change from symbols to numbers to do with frequencies, the formulas give frequencies in radians per second, and the numbers you want to come out in hertz, and there's a 2 pi in between. So when you substitute numbers, you've got a 1 over 2 pi, and it's convenient to remember that 1,000 over 2 pi is 159. Saves you one keystroke. And 160 is usually good enough anyway. And if you have the capacitance in microfarads and the resistance in K, this gives you the result in hertz with 159 in the numerator. However, the important part about this, as I emphasized before, it's worthwhile writing down the intermediate numerical result before you combine all the terms, because that way you retain the usefulness of the low entropy version. And when you do that in this case for the two results, you see that the resistance that determines the omega 1 is principally the R1 parallel RL. The R2 is almost negligible. In the other case, since it's a triple parallel combination, the R2 is the dominant one because that's much the smallest of the three. The result comes out, the two roots are 47 Hertz and 82 kilohertz, which verifies the two roots are not only real, but well separated, which is the consequence of a very small value of Q. So here's the assembled results. This is now the factored quadratic in the denominator, where these are the approximate real root factors, assuming the f is equal to 1. And you see, no radical sign. Here are the two roots. Here's simply a listing of the zero frequency gain and the three corner frequencies. The zero is already explicit, and these are the two simple ones that come out from the quadratic solution as the assembled numerical values also. So, again, to compare this result with the conventional one, and this is what we had in the introduction at the beginning, the conventional result is high entropy. The symbols don't tell you anything. The low entropy result shows you immediately that the two capacitors don't interact. C1 determines one corner, C2 determines the other. And in fact, there's almost no interaction between the resistances either, because R2 is negligible in omega 1, R2 dominates omega 3. Well, even this is more work than necessary. Let's talk about a still better solution. And you latch onto this one right away because it's probably what most of you do anyway. Look at the original model after Thevenin reduction, because that's always a benefit anyway. No, sorry, this is before Thevenin reduction. Doesn't make any difference. Simply look at the circuit and ask yourself qualitatively what happens as frequency goes from 0 to infinity. What happens is, at 0 frequency, the two caps are open. So you have a simple resistive divider, so you can write down what the 0 frequency flat gain asymptote is. It's just that resistive divider. As frequency increases, the reactances of the two caps start to come down from infinity. As the reactance comes down, because C1 is 50 times bigger than C2, the reactance of C2 is 50 times bigger than that of C1. So even though they're effectively in parallel, the C2 isn't doing anything. So you could throw it out, which is equivalent to dumping the second part of that middle coefficient, based on the same approximation, which I already mentioned is less than a 2% error. So forget C2 while the reactance of C1 comes down. Now, as it comes down to be comparable with R1 and RL, of course, it's going to start bypassing the RL, so the 0 frequency flat gain is going to start dropping off. So there's going to be a pole somewhere because of the C1, C2 being negligible. The next thing that happens is the reactance of C1 comes down until it approaches 1K, in which case the total impedance of that branch starts to level off at 1K as the reactance of C1 drops below it. The reactance of C2 is still 50K, so it's still negligible. So as the reactance of C1 comes down, that slope in the gain will level off. That's a 0, a concave upwards corner. Again, dominated by C1 only. At that point, the circuit is now such that C1 acts as a short and C2 is still open. So you get another flat gain corresponding to a different resistive divider, where R2 is in parallel with RL in the bottom branch. Finally, at a still higher frequency, the reactance of C2 comes down to be about 1K. Then it causes the gain to fall off again. From its already lower value, it falls off even more. But only C2 is doing anything in that frequency range. So you see right away that you can divide the result into two separate frequency ranges. In the lower range, only the C1 does anything, and it causes both a pole and a zero. And you can solve that part of the circuit separately. After that, the C1 becomes a short, and then C2 starts to come in, causing the second pole. So qualitatively, before you even write anything, you know that the two poles are determined separately by the two capacitors. And the approximation of dividing the result into two frequency ranges is equivalent to making the approximation that the two real roots of the quadratic are well separated. It's the same approximation. So the solution finally can be written by solving the two pieces separately. This part of it is the same lag lead network we talked about before after you make the Thevenin reduction. So you get a zero frequency flat gain and a normal pole and zero, or you get a high frequency flat gain and an inverted pole and zero, and you can write these results down directly. There's the numerical values. The second part of the solution, the C1 is now a short. We've already made the Thevenin reduction. Now the C2 comes in, make another Thevenin reduction, and you get another building block circuit, the single pole circuit, in which you have already a low entropy version of the effective resistance directly from the Thevenin reduction. And then you piece the two results together. The final result is the product of both sets, and there's the answer, either in normal pole zero format or using the mid-band gain as the reference. And here's the final result: asymptote and phase sketches, labeled with salient features, both in low entropy expressions and with numerical values, both magnitude and phase. Notice that there's an overlap of the phase asymptotes in both cases. So that's the answer to the original formation of the problem. Sketch magnitude and phase asymptotes, label salient features with both low entropy expressions and numerical values. Makes a very compact summary of the result. I mentioned that this was the homework problem at the very beginning of the school year, and of course they come in with the high entropy results, the inaccurate numerical values, and so on. Then they get the same problem later in the term, and most of them come up with something pretty close to this, which is great. Notice, if I backed up a couple of pictures, that there's almost no algebra. The results are mostly written in one or two lines. And everything is there. Everything is summarized on this graph, both analytically, low entropy, and numerically. Now, not only do they get the same problem later on, which gets them to this point, but there is a part two of the problem this time, which is a design problem, which is of the nature, imagine that you're going to use this as some little more complicated compensation network in a feedback system. So you have to be careful about maximum phase lag before it goes away again. Notice that with the numbers we get phase overlap such that there's a phase lag of 68 degrees over this particular frequency range. Now imagine that the design problem is you want to prevent the maximum phase lag from exceeding 50 degrees at any frequency. Change the values to achieve that. Now, again, subject to the limitations of homework problems, you have to constrain it more than that. So I tell them, change only R2. Because R2 determines one of these corner frequencies, so I can change the overlap. They have to do something else as well, because the phase angle is always going to go to minus 90 at infinite frequency with this circuit, regardless of what you change. So in order to bring that back from 90, you actually have to add another element. You have to put another resistor in series with the second capacitor. And all that does is duplicate the problem. Now, up here, you get another phase lead because of the extra resistor. So you simply do the same problem twice now to make both of the maximum phase lags not greater than 50 degrees. And of course, it's easy to do that because you start with a known value of the maximum phase lag, and according to that little handbook formula we had earlier on, you can translate that directly into the required ratio of these two corner frequencies, which is the first pole and the zero. And since we have these nice low entropy expressions for the pole and the zero, you can solve the ratio for a different value of R2 that gives that result. And then you do the same thing again at the higher frequency range in terms of the new resistor. And that's very easy to do. But if you had the first pole in terms of the conventional quadratic formula, you couldn't do that, because you couldn't solve it in reverse for the R2. So that points out very clearly that from a design point of view, which is all we really care about in the long run anyway, the low entropy results make the difference between being able to do it and not being able to do it. That's really the bottom line of this whole thing. So that's been a fairly extensive diversion from this particular example to talk about quadratics, but I like to do it that way. I like to introduce a generality by means of a specific example, develop the generality, and then go back to the example as an application. I think it helps to keep the motivation in mind as to why these generalities are worth talking about. When you do them in isolation, you don't see why they're any use. So it's always good to introduce them by means of examples.